Hello, folks over in 111 land. I know it's a snow day. Unfortunately, we don't have the benefit of being able to just drop everything in this day. So, watch this video. Hopefully, it won't take the whole time, but I'm going to try to finish chapter 1. And we'll go over some more practice problems on Friday, assuming we have class on Friday. But don't forget to join the Achieve. I know even if you don't have the access code, you should be able to get free access for like 2 weeks. There's no excuse to not join the Achieve. You gotta create an account, and then you'll put in the course code to find the course, and then if you have the access code, you'd put in the access code then. If not, start your grace period, your 14-day grace period to sort things out and get the access code. But so assignments are already been due. So join up. I only have 9 people there. I don't know why. Don't have more, but come on, folks, come on. But we're going to finish chapter 1. Chapter 1 where we're going to look at our among other things, we're going to look at dimensional analysis. Dimensional analysis being the method by which we do a lot of our math. So, please pay attention. We're going to try along some of these problems with me. Try along. I know it's not always easy. That's why we're going to work some of these out. And then we'll work out some more on Friday, because if we can't figure this out now, you really need to come and see me. This is going to only build from here. If you understand this now, we will take this moving forward. If we don't understand it now, you'll struggle now, and you'll struggle later, and then maybe you'll learn it later, maybe you won't. Hopefully, if you learn it now, it'll stick with us later. Okay, with that in mind, dimensional analysis. This is basically the process by which we convert one unit into another. It's the mathematical treatment by which we show how a conversion gets done. Now, there's formulas you could memorize where you plug in the values for each unit and you work them together. But typically what I will do is I will set up a problem using dimensional analysis so that units, if we multiply them together, they will combine. If we divide them, they will cancel out. As you can see here, if I'm calculating the area of a room, units of area is meters squared. To calculate the area, 10 meters by 20 meters, I'm setting up 10 meters over 1 and 20 meters over 1. 10 times 20 is 200. But meters times meters, any unit, any variable that is multiplied by itself is essentially raised to the exponent of 1. Anytime you multiply anything that's raised to the exponent of 1 by another thing that's raised to the exponent of 1, we add those two exponents together. 1 plus 1 is 2. So, meters to the first times meters to the first becomes meters to the second. They've combined together, not able to cancel out. If I'm calculating density, density is grams per milliliters one way. If I have 5 grams of solid and a volume of 1.85 milliliters, to get density of grams per milliliter, I am dividing 5 grams over 1 by 1 over 1.85. Grams, 5 grams times 1 is 5. 1 times 1.85 is 1.85. 5 divided by 1.85 is 2.7. Grams divided by milliliters, they are two different units. They are not allowed to cancel. And so because they're not allowed to cancel, they just carry over, and I have grams over milliliters, which is the correct units for density. But generally speaking, when two units are the same type on the opposite sides, they will cancel. So if I divided grams by grams, grams would cancel. Now when two units are the same type on the same side, they combine as the meters by meters. And any units that are left after the calculation must match the units of the desired answer. That is one way to confirm we are done. If I'm looking at an area that no matter what the units are, it should be a length squared, length times width, a distance squared. If I'm looking at a volume, it should either be a volume in liters, milliliters, something like that, or in meters cubed or centimeters cubed or some sort of cubic distance. Now, here's how I'm going to treat most of these math problems. I start with my conversions. I start by writing my given value over 1 with its units over 1. Why do I write it over 1? Well, the first thing to note is that any number over 1 is itself. But by writing it over 1, I'm telling myself this is going to be on the top part of the equation. The 1 is on the bottom. I'm going to multiply by some conversion factor that cancels out my given units of my starting and converts me closer to my desired units. So, if I'm turning meters into centimeters, and I start with meters, I'd start with meters over 1, and then I'd know I want centimeters on top and meters on bottom on my conversion factor. Because I know the meters started on top, so I need, in the next step, the meters to be on bottom. I want to get closer to centimeters, so I should want the centimeters on top in my conversion factor. Now, if I have to do multiple conversions to get to where I need to go, try to plan out your steps so that each conversion cancels the last. You might not know how many seconds are in an hour, but you should know how many seconds are in a minute. And we should know how many minutes are in an hour. So I would go, if I'm going seconds to hours, I'd go seconds to minutes, minutes to hours. Then I might go hours to days if I need to, days to weeks. That way, each guy cancels out the last. I don't have to do a really fancy conversion if I can do smaller conversions. Just like you can go inches to feet, feet to miles. So you don't have to do it all at once if you have to. Now, if your given value is a ratio, such as miles per hour, you may have to convert both the top and the bottom unit. But you can do it separately. You don't have to do, if I'm going miles per hour to kilometers or meters to seconds, for example, I might do all my conversions for miles to meters first. Then I might do all my conversions from hours to minutes. But I don't have to do it all in one conversion factor. I break it down to as many factors as I need to. And if you have an exponential unit, such as feet squared, you just have to do the same conversion factor multiple times. Like if I'm turning feet squared to inches squared, I'll just do there's 12 inches in 1 foot times 12 inches in 1 foot. Inches times inches is inches squared. Feet times feet is feet squared. So feet squared divided by feet squared would cancel out. So there is 144 inches squared in a foot squared. So here's some simple conversions. Before we go on, maybe pause this video. Pause this video, try to work these out. So 250 meters to kilometers. So I'd start with 250 meters over 1, and I'd have 1,000. You divide by 1,000 meters, but multiply by 1 kilometer. As you see right here, I'm going to go ahead and show the answers so that we can see this. So 250 meters, we have meters on bottom. They cancel out, have 1,000 meters, 1 kilometer. Kilometer is kept through, so the answer is 0.250 kilometers. When 13 yards is given turned to inches, I know there's 1 yard and 3 feet, and 1 foot, and 12 inches. So I'd start out 13 yards over 1. Now to get rid of my yards to feet, so those would cancel out. Get rid of my feet. As we go to inches, the feet would cancel out. So the net math is 13 times 3 times 12, which would give us inches. Now, since there's only 2 significant figures here, I can only keep 2 significant figures in my answer, so even though the number is 468, we should round to 470. Now you may say, well, there's only 1 sig fig in the 3 feet to yards. However, this is a exact conversion. It's a definition. So this is considered to have infinite significant digits. Same as here. Any exact number, any definition number is said to have unlimited sig figs. So the sig figs here controls the sig figs there. If I'm going millimeters of mercury to torr, well, there's 760 millimeters of mercury per 1 atmosphere. And there's 760 torr in 1 atmosphere. So setting that up, millimeters of mercury, millimeters of mercury. Atmosphere, atmosphere. The final unit is torr. 760 divided by 760 is 1, so you get 35 torr. That's a little silly, but a millimeter of mercury, we'll learn about this more later, is the way we physically measure a barometer. The barometer was invented by Torricelli. The torr is named after the barometric unit that we use to measure a barometer. So they're essentially the same thing. That's why it didn't change. Finally, 5 centimeters squared to inches squared. Well, there's an exact conversion of 2.54 centimeters in 1 inch. So we set that up. 5 centimeters squared, 2.54 centimeters per inch squared. Do that twice. Centimeter, centimeter squared, cancel. And we get inches, inches squared. So 5 divided by 2.54 divided by 2.54 again gives us 0.78 inches squared. Don't worry if this is going a little fast. We're going to do some problems straight from the Achieve. So if you go to your Achieve assignment, I'll work them along with you. The last couple slides, density and temperature. 2 equations that we will see. I will give you these equations when it comes test time, but we should be able to use them. Density is simply the ratio of mass to volume in an object. It's an intrinsic property. It doesn't depend on the amount of matter. A lot of cork or little cork will still float because it has the same density. 1,000 pounds of cork will still float. It's just going to be a lot of floating cork. We can use density to determine the chemical identity of a substance. So if you measure the density of a metal, you can determine what type of metal it is based on how much volume a certain weight displaces. But dimensional analysis will allow us to convert mass to a volume to a mass if we have a density. And if we don't have a density, but we have a mass and a volume, we can calculate density. The main equation is density equals mass over volume. But by rearranging this, by either multiplying volume to the other side, we get mass is equal to density times volume. And then moving the density to the other side, volume equals mass over density. So grams divided by grams per milliliters gives us milliliters. Grams per milliliters times milliliters gives us grams. Or grams divided by milliliters gives us grams over milliliters. By watching our units, these conversions should make sense. The other thing is temperature. Temperature is the measurement of heat flow to and from an object. Now the SI unit is Kelvin. We will often use Kelvin preferentially, but there's sometimes it doesn't matter. But to calculate Kelvin to Celsius, we add the number 273.15 onto the Celsius value. So even when it's freezing out, it is still 273.15 degrees Kelvin. When it's room temperature, which is typically considered to be 25 degrees Celsius, it would still be something like 298 Kelvin. So, why do we add 273.15? Well, because Kelvin is defined as the value that the zero value for Kelvin is the absolute lowest temperature that can exist in the universe. If we reach 0 Kelvin, all motion stops, even on the atomic level. Even when things are frozen, the atoms are vibrating. The ice molecules are vibrating. Even though it's frozen, they're still shaking a little bit, like shivering atoms. As they get colder, they vibrate less and less and less till get to the point where we hit 0 Kelvin when all molecular motion stops. And that would be negative 273.15 degrees Celsius. So we're simply just working from 0 Kelvin back to Celsius. Kelvin was discovered after the Celsius and Fahrenheit scale. But now, if we were to have to convert between Fahrenheit to Celsius or Celsius to Fahrenheit, there is an equation you can learn. I will often give you at least one version of this equation on a test. Celsius is equal to 5 over 9 times, in parentheses, the Fahrenheit value minus 32. So remember, freezing point in Fahrenheit is 32. So 32 minus 32 is 0. Then 0 minus 5 over 9, because that's 0 degrees Celsius. But any temperature, so 98 degrees Fahrenheit, what's that value in Celsius? What's the human body temperature in Celsius? Well, 98 minus 32 is 66. Then I multiply by 5 divided by 9, and I get 36.6 repeating degrees Celsius. So 36, almost 37 degrees Celsius is the human body temperature. So we can convert back and forth. To get the other equation, you would multiply Celsius by 9 over 5, and then add 32 onto that value to get the temperature in Fahrenheit. So last set of problems, and then we're finished with this chapter. Maybe pause the video now, try these problems. Otherwise, just skip on forward. So 13 grams of aluminum with a density of 2.7 grams per milliliter. How much volume would this take up? So I have a mass, I have a density, and I am asking for a volume. So what am I got to do? What do I got to do? I start with my 13 grams over 1, and I'm going to divide by 2.7 grams over 1 mil. When I divide by a fraction, it's the same as inverting the fraction. So 1 mil on top, 2.7 grams on bottom. Grams over grams cancel. Milliliters are all that remains. 13 divided by 2.7 is 4.8 mils. Okay, the next one. I have 32 mils of 0.93 grams per milliliter density olive oil. How much would that weigh? So I have a volume, I have a density. Volume times density equals mass, but if I want grams, I start with 32 mils over 1, and I need to cancel out mils, so I'm going to multiply by 0.93 grams over 1 mil. So mils over mils cancels, and 32 times 0.93 gives us 30 grams. It weighs close enough to 30 grams. Final problem, at what temperature Fahrenheit would 150 Kelvin occur? Unfortunately, there is not a convenient way to turn Kelvin directly into Fahrenheit, so we must go through Celsius first. So the first step is to subtract 273.15 from my 150 degrees Fahrenheit, Kelvin. When I subtract, I'll get negative 123 degrees Celsius. Now, 123. Now, as I said, to that number, we would multiply 9 over 5 and then add 32. So, multiply 9 over 5, and then we add positive 32 to the negative number, and so we get, that'd be negative 190 degrees Fahrenheit. Both of those numbers are really cold. We're not going to see them very often, so don't worry so much about them. But that would be temperatures at which maybe we're going to start freezing out some of the gases that we might normally see. Now, here's where we're going to start looking at some actual problems. Okay, so looking at this real quick, I'm going to start with problem number 19 on the chapter 1 homework. My problem says convert a speed of 987 miles per hour to units of feet per minute, and they both give you a place to plug in the factors, and then ask you to actually do the conversion. So we want to go to, by the end, feet per minute. So it doesn't matter which order you do it, whether I put hours to minutes first, or I put in miles to feet first. I'm going to go ahead and do the hours to minutes. So, since there's hours here, I want to have hours here. There's how many minutes an hour? There's in 1 hour, 60 minutes. By putting that there, hours and hours are canceled. Now, the next step is to go from miles to feet. Miles is the big number, so 1 mile is going to go down here. And in feet, there is 5,280 feet. If you're unsure of the conversion, you can look it up. Miles and miles cancel out. Now to get my answer, what do I got to do? I got to multiply everything on top. So I'm going to say 987 times 1, I'm going to leave the 1 off, times 5280. Now I got to divide by everything on bottom. I have a 1, I have a 60, I have a 1, so I'm going to divide by 60. And I get number 86856. Now, if I'm being sig fig accurate, 3 sig figs here means I can only have 3 sig figs here. So it would be 86900. Now, I don't think it really matters, but we'll go ahead and see. Okay, plugging in my number just to see whether it's going to be annoying or not. Okay. So I'm plugging in 86900, checking answer, and boop, it's good. Now, mind you, the homework has a built-in way of a built-in error percentage, where it's going to take whatever the right number is, or what it declares the right number is, and gives you a 5% or some thereabouts leeway of up or down. So if you miss it by less than 5%, it will still mark it correct. Now, how different is my 86856 from my 86900? 86900, then I'm going to divide by my 86856 times 100, and then that's less than 5%. It's actually less than 0.05% error. So it's really not that big of a change. So much so that it can safely ignore it. My next problem simply states, Steve races to the nearest taco stand at lunchtime and sees his pedometer recorded his speed as 108.7 centimeters per second. And he wants to know what was his peak speed in kilometers per hour. So I'm going to convert this to km per hour. So here's how I'm going to do it. I could go it in 1, but we're going to go it slowly. Now, first step is to convert to meters. 1 meter is 100 centimeters. Doing that, I'm going to cancel my centimeters. Then there is 1,000 meters in 1 kilometer. Meters, meters. That has been converted. So now I have that. That is matched up. Now there is 60 seconds in 1 minute. Seconds, seconds. And there is 60 minutes in 1 hour. Minutes cancels minutes. So now I'm left with just units of hours and kilometers. Kilometers per hour. I've done all my conversions. So now I just need to multiply everything on top and divide by everything on bottom. So once again, start with my 108.7 times 60 times 60 divided by 100 divided by 1,000. And I get 3.9132. But once again, 1, 2, 3, 4. 1, 2, 3, 4. I can round there. That would be the best number. However, most times, unless the program physically asks you to the correct number of significant figures, more significant figures will not hurt you. Less may, but more will never hurt you. Now, problem 21. Mercury, also known as quicksilver, is a metallic element liquid at room temperature. Calculate mercury's density if the sample is found to have a mass of 705.0 grams. That's our mass. And a volume of 51.72 milliliters. That's our volume. And it wants the density in grams per milliliter. So I want a density of grams over milliliters. So I'm going to go, okay, so what do I got to do? 7,050 grams. So the first thing we note, grams and grams are on the right side. Then I got to divide by my milliliters. So I'm going to divide by my 51.72 milliliters. Grams on the right side, milliliters on the right side. Neither of them cancel. So I could have written it like this. However, by putting them in fractions, I can definitely see where each unit ends up. Milliliters ends up on the bottom, grams ends up at the top. By doing it like this, I can see grams, milliliters. This I have to do a couple more steps in my head. So, let's solve this. 7,050 divided by 51.72. Do this math, and I get 13.63 yada yada yada. But 4 sig figs, 1, 2, 3, 4. 4 sig figs, 1, 2, 3, 4. We're going to round to 4 sig figs. That tells me I don't need all those numbers. I just need the first 4 numbers. So I'll type in 13.63. Now, mind you, if you have mercury in your answer, that's the answer. Your density will probably not change. But if you have another set of numbers, follow your set. I'm showing you a generic problem, how to solve this. Your problem may be slightly different. Always go based on your problem. But the way you solve it will be very similar. So the last problem of this assignment, problem 22, the surface temperature of Venus may approach 755 degrees Kelvin. They want to know what is this number in Celsius. They want us to convert this into Celsius. Then they say the temperature on Mercury drops to negative 271 degrees Fahrenheit, and they want us to convert that to Celsius. So let's solve those. Well, this one, the equation is Kelvin minus 273.15 equals Celsius. So we have 755 minus 273.15. Since this only goes to 3, the ones place, our answer only needs to go to the ones place. 755 minus 273 gives us 482 degrees Celsius. Venus is very hot, if you did not already know that. Not really livable for humans. Now, this equation, Fahrenheit minus 32, and then we multiply that by 5/9. So, step 1, negative 271 minus 32 is equal to negative 303. Now that number is going to be multiplied by 5/9. So negative 303 times 5 divided by 9 is negative 168.3. We're going to just round that to negative 168. So negative 168. Still very cold. Very cold. So if you do that, that's the last 4 problems of this assignment. The harder math problems of this assignment. So, just want to go through those. We will work on a couple more problems like this, assuming we have class on Friday. If we do not have class on Friday, I might work on a few problems, but I will start Chapter 2. Have a good day.